Okay. I think we are on. Pretty sure we're on. Chat. Let's get chat going. Hello. 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 That's on. It's cool. And we're just gonna message a group and say we're on. Cool. So I'm gonna chill out and see how many people show up. Feel free to say hi on the chat if you drop in. So today we're gonna we're gonna push on the pull request, the SPI work pull request. Um, Most of what we did last time was just to we talked about SPI and how it works and kind of um, the way it works and everything. So today what we're actually going to do is just go through what we talked about last time and basically write the code for it to make it work. Um, Feel free to ask any questions. Feel free to interrupt me when you can via the chat or via WhatsApp if you do have if you're on the group. Yeah, so let's boot up our IDE and see where we wanna be. STM. Let's see. Is anything open? Okay, cool. STM IDE 32Q back. Okay, cool. While that starts up, let's look at our comments from file exchange from last time. So nice. We built a SPI header file. We built a register definition for the SPI registers that we're going to use for configuration and for basically writing and reading. And we built a SPI source file that we're going to use as we implement the APIs that we're going to want to we're going to kind of release for this. Okay, awesome. So let's look. So what's we're kind of going to dive straight into the deep end and start getting things done. I think it's fair enough. Like I think anyone who needs to join will join at an appropriate time, and we can always like catch them later. They can catch us later with their questions. Feel free to leave questions in the chat. Let's see if the IDE has booted up. The IDE is on. I think the text is big enough. We can see. So let's go with the fast kind of change we're going to make. So I think the first place we're going to go is I think the header file. And in the header file, we're going to define a couple of things. We're going to define what are we going to define in the SPI header file? Let's see. SPI header. So we need a handle. Let me just check through my notes. Okay, cool. So we need a config struct to help us do the configuration, and then we also need a handle structure to config struct, basically for us to do the configurable items for SPI. So this is device mode, whether slave or master, bus configuration, clock speed, all of those kind of things. And then we need another struct that holds the previous struct that we can now use if we want to say run SPI1, SPI2, if that makes any sense. So let's build type def struct. I actually want my things to be on this side, and then let's name this one SPI config t. Yeah, so this is the configuration struct, and the items we want here is int t. Do I need to include that will come to? So SPI device mode. So this is it a master or is it a slave? Int 8t, and then let's go SPI. Let's do boss config. So this is kind of like how is it like, is it full duplex, half duplex, and 18, and then we want SPI clock speed, CLK speed. So what baud rate are we using? And then we want int 8t SPI data frame format, int 8t. Let's do clock polarity, simple, and then int 8t. Let's do SPI clock phase. I think int 8t. Let's do SPI slave management. Okay, cool. So with this, we can basically configure SPI as described in the document, in this document. So we have this configurable items. Sorry, I keep covering my mouth. That's really bad. So this one, if we go here, in general, we have basically the slave select, clock phase, and polarity. We have a data frame format, and the rest of the stuff we can basically we discussed last time. Sorry. Okay, cool. So all the configurable items are here, and we can use this config key to configure an SPI peripheral, say like so configurable items for SPI X. So now let's make a handle structure use. Okay, so we're gonna type def struct, and then in here we're gonna, I think in this struct we're gonna have a SPI reg def t. So this is a pointer to basically, this will be a memory location. Okay, so if we want to have in here, you can pass in the base address for say SPI1 or SPI2 or SPI3, which means we can now how do I say it? We can actually decide, do we want to use SPI1, SPI2, SPI3 from this handle structure, and then we'll pass in the SPI peripheral that we want to use, and then the configuration we want to use on that SPI peripheral. I must say SPI config. Sorry, I'm gonna make a note. Fix left armrest. My left armrest is loose, so it kind of makes some noise. I'm sorry about that. We'll just have to deal with that for this stream, but by next one I should have that sorted. So cool. we've made SPI header file. I mean, SPI header file with the configurable items and the handle structure. So the next thing we're going to do is actually after that, I think let's populate our source file. And first of all, we can actually just do a cursory build to see if this actually does build. Sorry, I need to look at the comments, see if there's any questions. Cool. No questions. Cool. So does build successfully. Doesn't seem like we have any errors. Cool. So no. What's the next thing? So SPI. Let's add prototypes for the APIs that we want to have in SPI. So let's think about it. So we want to be able to, and this is gonna be SPI handle T. That's cool. Yeah, awesome. So init and the init APIs. Okay, so void SPI init. This will take a SPI handle T PSPI pointer to SPI handle. Okay, cool. And then we need a dinit that will do the same thing. Well, dinit will basically, this will do the same thing, but it will actually this can PSPIX. This can just take a regdef. So it can just take the memory location of which SPI we want to turn off. Cool. Let's add some clock setup macros. So because we need to be able to activate the clock for whatever SPI, how do I say it? Peripheral we want to do. So if you want to use a peripheral, you have to enable its clock. This is so that we don't waste power. So we need an API to enable and disable clocks for whichever peripheral we want to use. Sorry, I keep looking at the comments, but okay, and then I'll scroll down a little so we are like in the code. And we're gonna take the base address of the peripheral we want to do, and we want which is en or bi. So yeah, cool. So now, and then we need to do the send and receive APIs. Send and receive APIs. So TX and RX APIs. So void. Wait, how can we send transmit sequence? What does the transmit sequence? Comments? Okay, cool, no comments. So let's send data. Transmit sequence begins when a byte is written into the TX buffer. The data byte is parallel loaded into the shift register from the internal bus. Okay. So DR. It's a 16-bit register, and you can write words into it. So either half words or words. Okay, cool. So void SPI send data. This will take an SPI peripheral, so regdef. SPI. Okay, and then this will take we need a buffer. We need a buffer of 8 bits, so we can send to. Okay, int 18. And then we also need to specify len. How much data are we sending? We need to specify that, all those. Okay, void SPI save receive IE or EI receive data. And basically, I think the parameters can be the same as the one before. So you need to know which peripheral you're sending, you're receiving in. You need to know, you need to know where to write what you're receiving, and then you need to know what length you're receiving. Okay, and then I think we need interrupt stuff. SPI interrupt configs. Okay, cool. So void SPI IRQ config. So this is to configure interrupt requests for the int 18. So here we're going to take the IRQ number. And then we want uint int 18 en or di. Okay. IRQ priority config. And then what do we take here? Number and priority. So almost same as this, but the second one is IRQ priority. Okay. And then IRQ handler. Some way to define the IRQ handler. Which handler? Ping handler. Okay, so let's build that. Okay, cool. So I'll just quickly commit what we've just done. Okay, cool. So far, any questions? If you have any questions, please feel free to like put them on the chat or on WhatsApp as I take some tea and check the other groups. Um, okay, cool. So we are live. It is going. Cool. Amazing. Uh, so what's the other thing we need to do now? We need to start defining. So since I don't have any questions, I'm just gonna keep on. Um, we need to start defining like how do we how do we just a moment as I get this. I kind of lost my train of thought. We need to start defining the the prototypes that we just defined. We need to start defining their functions. But before we get to do that, we might have to define a couple of macros that are going to be useful for that. Okay, so let's go to our header file, our how do I say it? And let's go to our device header file. So, perfect. And in here, we have SPI register definition, cool. And we do have peripheral definitions for SPI1, SPI2, SPI3. We have clock enabled for alternate function, GPIO. So what we need to do actually, I think right now, is we need to do um, we need to do what did I say? We need to add some. I'm confused. Just a moment. Let me look at the documentation. So, functional description. No. SPI functional description. Configuring SPI in slave mode. Do we start in slave mode or master mode? Okay, cool. So, set the DFF bit, select the C pole and the C phase and the data frame format and the hardware mode. And so basically, I need to go to init, but I need to do the clockwork. I need to do the clockwork, the stuff that like fixes the clock. Um, okay, cool. So first of all, in order to disable, we need register reset macros. Yeah, this, you see. Where do we use this? Where do we use this? Init. Just a moment. GPIO source GPIO are we using them for the init? Registered. Okay, cool. So let's start by fixing the init. Okay. So we're basically going to start with the init. And the init, we need to be able to initialize, basically go back to the beginning for the SPI registers. And this SPI register, the map for where to reset the map for where to reset the clocks for the map on where to reset the clocks for the SPI peripherals is in the RCC clock controls. Cool. So let's go to RCC registers, and I think so. First of all, let's find out where is the device header file. So let's find out the so SPI 1, 2, and 3. Okay, cool. So where are those? Where are the peripherals located? Okay, SPI. Okay, SPI 1 is on APB2. SPI 1, APB2, SPI 2, and 3 are on APB1. Okay, so we need to go to APB2 and APB1 and see which bits are used to reset SPI. Cool. Let's look at APB1 reset register. APB1 reset register. So APB1 has a reset register. So this is a register where if you write to this register, to a bit in this register, you're wanting to reset some peripheral. Okay, cool. So let's look for SPI 3 and 2. Okay, bit 14 and 15 are for resetting SPI 1 and 2. So SPI bit 15, bit 14, bit 14, bit 15. Bit 15 resets, no effect if it's reset. If it's set, it resets SPI 3. Bit 14, 0, no effect, 1 resets SPI 3. So let's quickly add macros in our header file, in our device specific header file, to MCU specific header file. Oh my word, I get so lost. There's a lot of things. In our MCU specific header file to now reset SPIs. Okay. So SPI register reset macros. Let's just see macros that do the. Oh yeah. Nice. I just got a comment. I'm Cardinali. Probably Eric. Is it Eric? I don't know. Who is it? I don't know. Anyways, wherever you are, thanks for being on the stream. Okay, cool. So it's 15 and 14 for SPI 1, SPI 2, SPI 3 and 2, and then there's another one for SPI 1. So hash define SPI 1 register reset. Okay, I'll just copy that 3 times. I'm lazy. Okay, SPI 1, SPI 2, SPI 3. Okay, cool. And then here we're gonna do actually on the tab first, and then and then yeah, I want to finish whole thing, and then I want to go to RCC and then dot APB APB. Okay, so there's something in my RCC struct that is not right. Do I not have an RCC struct? Yeah, APB2 reset, APB1 reset. Okay. APB2 reset. Oh, it's because I'm trying to do this. RCC dot APB PB APB 2 as RS APB2 RSTR. Okay, and then we want to set 1. So for SPI1, I think we're on 12. I can quickly confirm that. APB2 beat 12. SPI1 reset. Okay, cool. So we want to reset this. We want to reset this. Blah, 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 blah. Mm, mm. I'm just going to copy that because it's way easier to copy. So, but what I'm doing is evident. I'm setting an item and then I'm going back and resetting it. Like I'm setting it to reset the I'm setting the sometimes I can't code and think at the same time. So I'm setting the is it 2 or 12? I think it's 12. I think it's 12. I think it's 12. That's not good. That's not good. That's 12. That's 14. I will explain this after I stop talking, after I figure it out. But now I think if I talk and code this part, I will be doing you guys an injustice. So, and this is 15. APB1, reset register, APB1, APB1. Okay, cool. And this is 14, and this is 15. 14, 15. So SPI1, SPI2. Okay, cool. Perfect. So, in order to reset the register, we want to the default value of the field of the bit field so say SPI1 reset is 0. We set it to 1, which resets SPI1, and then we reset it to 0, so we leave it as we found it, basically. And that way we don't leave like unintended side consequences when someone else is trying to use them. That peripheral, and it's appearing like it's not working. Cool. I'm gonna check for comments and questions, and then I'm gonna keep going. More YouTube questions? No more YouTube questions. Cool. So let's, number 1, as always, after adding some code, build your code and see if it all works out. That seems to have fixed what we wanted. That seems to have added the code that we want. Let's now implement how to control the clock. Basically enabling or disabling the clock for an SPI. Okay, the first thing when you want to use SPI, so say you're at the MCU specific level, you want to use SPI peripheral. and that is either SPI1, SPI2, or SPI3. We need to enable the clock for SPI1, SPI2, or 3. That's like basically enabling the clock is almost like you need to enable power to that device so that it can go on. And let's first find out. The first thing we probably need to do is see where if we can add. You see, we've got like clock enables for clock enable and disable. What we need to do is find out which bits we need to do for SPI1 and SPI2 and 3. And then we need to add clock enable and disable. And then we need to go back and add the functionality of this to our source file, the pclock control function. So let's start by defining our clock enable and disable. Let's find out where we need to look for clock enable and disable. So I would look clock enable register for APB1, clock enable register for ENR, ENR. Okay, cool. So let's look for APB2, SPI2 and 3 are going to be 12 SPI1. Am I looking at the wrong thing? Okay, APB2 clock SPI1 is 12, SPI2 SPI1 APB2 SPI2 SPI3 SPI1 is 12, SPI2 and 3 are going to be in APB1, and they're going to be 14 and 15 again. ENR. Okay. 14 for 2, 15 for 3. Okay, cool. So now let's define some quick macros here. To APB2. Okay, cool. So let's define some quick macros here to enable SPI. So define SPI1 clock pclock en, and then I'll copy that twice. This 2, 3. Okay, cool. And then this will be RCC RCC SPI1 is in APB2 ENR APB2 ENR, and then we need to set the 12th bit. 12. Okay, because it's a double digit. Sorry, I'm just like wondering how come I broke my code there, but I didn't. Okay, cool. So APB2, APB3, APB2, APB1, and then it is R14 and R15. Okay, cool. So what have we done? We've just added macros to enable the clock. So now we need to add the same macros to disable the clock. It's very important to enable the clock and disable the clock for peripherals because this is how you basically, how do I say this? Power consumption, clock. When you're running the clock of a system, it's of a peripheral, it's active. if you're not running the clock, if you're not using a peripheral and you're running the clock for that peripheral, you're basically creating issues because not creating issues. Now, yes, you could be creating issues because you've activated a peripheral that's not being used, so it's a garbage in, garbage out kind of port. And also, you're consuming power. And when we're in embedded land, we don't want to unnecessarily consume power. So you want to enable and disable clocks as you need them. Basically, yeah, as you need them, when you need SPI for something, you kind of configure it, use it, and then after you're done with it, you clean it up, you close up, and you go. You're gonna end up with a very power safe, power safe. How do we call this? Power safe application, which is going to be rather awesome. So let's add some comments here. So 1, 2, 3. At FN is SPI clock CLK. SPI PCLK. CTRL. Okay. Brief enables or disables clock for SPI port. Yeah, and then params PSPI-X, what are we disabling? What params are we in EN or DI or DI? Are we enabling it or not? What does it return? It's a void return, and that's it. Cool. Let's now define the function. Void PSPI P clock CTRL, and then what do we take? We take a pointer to SPI register definition team PSPI X, and then uint 8 team EN or DI. Okay, cool. If EN equals to enable, cool. So let's implement that. If PSPIX equals to SPI1, and we defined SPI1, SPI2, SPI3. Yep, they're the base. So cool. And then in there, what do we want to do? We want to do SPI1 P clock EN. And then in our SPIH, did we define, or in our MCUH, did we define DIs as well? SPI EN. So this is DI. Oh wow. Checking for comments, questions. Cool. That's fine. SPIC here. EN. Okay. And then else. So we just copy this block. Else. uh, SPI1, SPI2, SPI3, 2, okay. Else, just do this. And then this is gonna be DI. Okay, cool. Let's build it. So in here we need to include, so we need to like this, in order to have, so that way, so that we can have all the, we can have number one, we can have the register definitions, and we can have the macros that we've defined here, like the volatile one, and also the integers we need to import this to the SPI header file. So we'll add that here. This should make it that our code built, finish building. Okay, cool. So that's good. That's done. There is no problem. So what did we just do? We implemented the clock control API. So now basically what we can do is we can enable or disable the clock for a specific SPI peripheral. Questions, comments? No, okay. None so far. Cool. Let's commit that and go on. Git status. Okay, amazing, amazing, amazing. If you're from South Africa or you've listened to 5FM in South Africa and you listen to the morning shows, there's an amazing sound. It's an amazing sound. Okay, cool. So I think I'm gonna finish this stream off with just defining some macros, some convenience macros that are going to help us when we're doing initialization of because we have so many options. We have options for whether it's a slave or a master. We have options for whether the bus is in full duplex, half duplex, or receive only. And then we have options for which clock speed we want to use. And then we have options for which do we want an 8-bit data frame format or a 16-bit one. And then we have options for clock polarity. We have options for clock phasing, and then we have options for slave management. So the last part I'm going to do about this for to finish off the hour of streaming today is I'm going to define the macros that we need when we are doing the initialization. And then next time we stream, I don't know. I could either stream next Monday or I could probably stream before the end of the week again. Just throw in a random quick hour there. I'll try and announce before. So send comments in YouTube and everywhere so that I know where to like announce if someone wants to keep along. But I'm going to define the macros that we need for polarity for all these options that we just did. For all these options that we just built, for all these options, which were the options I'm talking about right now. So this configurable options, device mode, bus configurations, clock speed, data frame format, polarity, phasing, and software slave management. I'm going to now define macros here, and then these macros are going to basically be used when we get to a point of actually implementing initialization. Okay, so let's do that and finish off this stream in a powerful mode. So device modes. Okay, so let's define SPI device mode master. Let's define SPI device mode slave bus modes. Oh, sorry. So this I'm defining macros now, so I need to give them values. When it's in master 1, slave 0. Cool. And master SPI bus SPIF bus config full duplex tab. This is gonna be 1. Okay, let's do a few more. Half duplex 2. This is like simplex RX only. That's gonna be 3. Okay, that's the next one. I can actually open this. There's something I can open, isn't it? Yeah, this one. Device mode, bus config, we've done. Let's do clock speed. Okay. SPI clock speed. I think we have 8 available options. You can divide from 2 all the way to 256. So fine. SPI as clock speed 2. Oh. Okay, now just 5, 6, 7, 8. Okay. This becomes 4, this 8, this 6, 16. This one becomes 32. This one becomes 64. This one becomes 128. This one becomes 256. That's the options we have right now. So let's give them values. 1, 2, 3, 4, 5, 6, 7. Okay, cool. So now let's go Boston clock speed data frame format. Okay. SPI, DFF, define. So this one we just have two, 8 bits or 8 bits or 16 bits, half words or words. SPI, DFF, 8 bits, 0, define, DFF, 16 bits, there's 1. Okay, so now we go to polarity. We have 2 as well. SPI polarity. Define cpol high. Define cpol low. One. Okay, so let's define clock polarity, clock phases. I can actually hide. I can just copy that. Phases. Okay, cool. So that's it. And simple software slave management. Slave management. SPI. Slave management. So okay, cool. I'm trying to see if we have any questions. Define SPI SSM EN. Define SPI SSM PR. Enable software slave manager, disable software slave management. Okay, so enabled is 1, disabled is gonna be 0. Okay, cool. And let's quickly, number 1, let's build that. Okay, it's building. So let's quickly commit that. Git status, git drivers, git commit -m. Enable add macros to make initialization of peripheral easier to read. Perfect. Git bug. Okay, so what have we done today? Today is the Wednesday, February 7th. So we defined the SPI prototypes, which were this. So we defined these prototypes, where is SPI header. We defined deinitialize APIs. We defined the clock setup prototype. We defined the send data and receive data prototypes. We defined the interrupt request configuration, priority configuration, and IRQ handling today. And then the other thing that we did, the next thing we did after that was we added macros to control SPI clock control. So this is to enable and disable the clock. So we added this, we added a few macros in the MCU specific header file, and these were these ones here, uh, these ones. So we added SPI 1, 2, 3, P clock, EN, and P clock disable, disable. So, and this is for enabling or disabling the clock when we need it. And then the next thing we did after that, we implemented clock control for the for SPI peripherals. So here it is, SPIC, and we implemented enable or disable for whichever peripheral that we are working with at the moment. Okay, and then lastly, after that, we added macros to make initialization of the peripheral easier to read. So we added these macros, we added this SPIH. We added all these macros to so that when we are doing device peripheral configuration, we already have the options defined for us, and we can just simply pick from there. Uh, that makes it easier, less to error prone. If we want to change something, we have to change it in only one places, and then wherever it's used, it can keep being used. I think I'm gonna knock off that stream there. It's been a good hour. It's been lovely coding with you guys. I'll try and see if I can do another stream before the end of this week. So maybe on Friday we can do the initialization of the peripheral. We can do peripheral and initialization probably. Um, implement uh, maybe peripheral initialization and send data, and then we can test. Initialization, and then we can probably test initialization and figure out a way of testing send data. That'll probably be where we add another device to the system. So we can add an STM32 probably F4, and we can probably see if we can send data to that device from the Bluepill and build up from there. This is exciting. I'll just chill around for any questions in case anyone has any questions. I'll check on the WhatsApp for any questions. Doesn't seem like it right now. And no questions on YouTube right now. So thank you all for coming for today. That was amazing. And I hope I see you next time. And let's cut it off from there. Yeah, feel free to, so what do I say? Feel free to kind of like leave comments asking for something I need to work on, or for uh, something you're more interested in seeing us build for this specific device. I want to build as much, if possible, cover the whole data sheet or reference manual for the driver. We want to build like a complete driver set for this thing, and yeah, explore embedded that way. Yeah, chilling. Awesome. Thank you all so much. That was amazing.